labor, so that when you apply for your actual job, you'll have some experience to apply with. Like, yeah, I mean, that's like,
Sorry, I think we're really internship. I guess like college do a lot of things like that. That's a little different though. It's more like a guarantee, right? That they're like not a bad employee.
yeah. Yeah, so I mean, yeah, internships are not usually probationary to full-time employee. They're almost always like fixed term. All right, so I guess we should talk about math. I mean, if you want to talk about this extra stuff, I'd be willing to talk about it if you want to know. In chat, what are we doing today? I thought maybe I would start by answering homework questions that people have. Let me point out, in case you have been so traumatized by the exam that you forgot to check WebAssign, there's 3 assignments sitting up there right now. So if there's any homework questions, I'm happy to answer those. I want to talk about the rest of 10.2, which means talking about area and surface area. I'm going to remind you what the rest of the operations we define for parametric equations are. And then if we have time, we will begin our adventures in polar coordinates, which will be a test of how well you remember trigonometry. But you all do. Where is everyone? Weird. Most people. 7, 11, 10, 15. There are 35 people enrolled in this class. There are 19 people in this room. There are 3 people online. What's that? It does. Point 4. Where is everyone? I mean, I know that I'm such a compelling lecturer. People just want to go on YouTube and watch me talk in front of a blackboard on their own time, but you're just more interactive when you're in a classroom, although less time. Okay, so are there questions I can answer about the homework? Yep.
I wrote several questions for, and it was like finding the tangent line. This is like what they did.
Okay. T cosine t, y t sine t, t is equal to pi?
Yeah.
Okay. So you have x is equal to t cosine t, and y is equal to t sine t, and they want to know the tangent line at t is equal to pi. Okay. So you remember the equation of a tangent line to a curve?
And it's the derivative.
Well, that's the slope of the tangent line.
Yeah. I don't remember the equation, but I was like, I found the slope.
Okay.
And I thought I found the slope wrong.
Well, so let's start. We'll do the slope and see if you get it. Let me write down the equation we're aiming for first. Okay. So the particular thing that we want to do here is we want an equation. If we're looking for a tangent line at x naught, y naught, so at some position on a curve, then we would never in a million years use the slope intercept form of a line to do this, because that would be crazy. Obviously, the way to go is point slope formula. That's easy to do. And then what are the different pieces represent here? So the x naught, y naught, that's the point that the tangent line is located at. And the m, the slope here, is given by the derivative at x naught and y naught. So we're going to get those pieces. And we need it all, right? Because if we have t is equal to pi, I'm going to need to find the anchor point, x naught, y naught. And then once I have that, I can plug it in. And then the derivative formula will also come from the parametric equation. So I guess the first thing we should say is that x of pi is equal to minus pi, I think. Pi times the cosine of pi, which is pi times minus 1, which is minus pi. And y of pi, so this point right here, this is like x naught in our equation. It's the x naught for the point that we're sticking the tangent line up to. Y of pi is pi times the sine of pi. Okay, why not? So I know I'm working at the point minus pi comma 0. At least we got that part. Find the slope. Well, m, since m comes from the derivative, is going to be dy dx, but we've got this formula parametrically, so we need to find dy dt divided by dx dt. And then we're going to take that and we're going to evaluate it at t is equal to pi when we're all finished. So let's compute some product rules. All right, so dy dt is d by dt of t sine t, which is the sine of t plus t times cosine of t. And if I take that and I evaluate it at t is equal to pi, I get sine pi times cosine of pi. That's 0, that's pi, that's -1, so minus pi, I believe. The x dt. So I'm being careful to separate my derivative calculation and my evaluation. It's like that's easy to get those all mashed together. Dx dt is d by dt of t cosine of t, and by the product rule that gets you cosine of t plus t times minus the sine of t. And if you evaluate that at t is equal to pi, you get -1 plus pi times 0, so it's -1. So if I wanted the slope, I just take the fraction of those guys. So that means that dy dt over dx dt evaluated at t equals to pi, it's just minus pi over -1. I got all the pieces. I know y naught, I know x naught, I know m. And so the line I'm looking for is y minus 0 is equal to pi times x minus pi plus pi. And I'm not sure if does WebAssign actually give you the opportunity to plug the whole thing in, or does it have it in the form y equals some blank box? Okay, well then we just okay. And if it didn't happen to be, if there happened to be a non-zero number here, you just add it to it. You don't actually have to sort this back out to y equals m. Like it loses information to do that. Okay. What is t cosine of t and t sine of t going to do? Are you going to get a spiral that runs out? Did anybody actually look at the graph of this thing? Oh, let's think about that for a second. Let's think about what this thing actually does. If the t's weren't there, just suppose we start at t equals 0, right? When t is equal to 0, what point are you at? 0, 0, right? Okay, so you start at 0, 0. Then when you get to t is equal to, so if you imagine the t's weren't here, this thing is rotating around a circle, right? Cosine t sine of t is the unit circle, but there's a t in here. So it's taking a point on the unit circle and it's multiplying it by a radius that's increasing. So at any point, your radius is equal to the angle that you have. And so I think you're basically going to do stuff like by the time you get to pi over 2, you should be here on the circle, but your radius is pi over 2. And then when you get to pi, the angle is pi, but the radius is bigger. And so I think what you're getting is something that like spirals away from the origin like this. You're crawling around the unit circle, but the t that's being multiplied in here is making you stretch as you go. And so, yeah. At least that's the general idea I have going on here. I could be wrong. The reason that it's not vertical here is because it's not actually a circle, it's increasing away. So that's what the tangent line looks like. Okay, anything else? Yep. 11, can you tell me what it is?
Yeah, x equals e to the t minus 9t,
Okay, x to t minus 9t.
and then y is L e to t over 2.
And the question says,
And you find an arc length.
find the arc length.
T is in between 0 and
Length where t goes from 0 to what?
5.
Okay, so if you remember the way that these arc length problems work, there has to be some sort of trick algebra that happens for this to be a thing you can actually integrate with them, right? Because you're going to be taking derivatives and they're going to be stuck underneath the square root sign. So there's definitely some kind of trick algebra that must happen. So let's see what it happens to be in this case. I'm going to predict you're going to write down dx dt and dy dt, and then when you put it all back together again, it's going to turn into something that factors like a quadratic. That's my guess about what's going to happen. So let's actually see. Let's compute ds. Doing arc length, we just compute ds first before we try to integrate it. ds is the square root of dx dt squared plus y dt squared dt. And what we're hoping is once we do this, we're going to get something that factors as a perfect square, so the square root disappears. Otherwise, this is not a problem we can do. Unless it's a trig substitution, in which case, you can grouse all you want about that. Okay, so what is dx dt? So dx dt turns out to be e to the t minus 9. And dy dt is 6 e to the t over 2. Make sense? Okay. Okay, so let's put it in here. So ds is the square root of e to the t minus, oh, I already know exactly what's going to happen. Here's what's going to happen. You're gonna multiply this out, and there's going to be a minus 18 e to the t in the middle, and then it's going to get added to a 36 e to the t in the middle, which is going to make it from a minus into a plus, and then you'll just refactor it in the perfect square. This is a trick you should have seen a million times when you did this in calculus 2. So if I take that and I square it and I add it to this thing squared, this turns, oh, that's a square right there. So this turns into e to the 2t minus 18 e to the t plus 81 plus 36 e to the t. Look, negative 18t e to the t plus 36 e to the t is positive 18 e to the t. This is the only way these problems work with this kind of trick algebra. Why does that matter? Because I know how to factor that. This is just this, but with a plus in the middle. So this refactors as e to the t plus 9 squared. Square root and the square disappear, and our final computation for, okay, minus 1, minus 1, minus 1, minus 1, not really minus 1 every time. You just get e to the t plus 9. So there's ds. And with these sorts of problems, it must be the case that the square roots get disappeared somehow, or you end up with something that a trig identity works on, because otherwise they're not integrals that can be solved, generally. Does algebra make sense? Hopefully, again, like it's suggestive of stuff you guys have seen before, because when you did the arc length section and the surface area section in Calc 2, it was just endless examples like this, where like some sort of magic algebra happened and the square root went away. All right, so what's the result here? Well, it means L is equal to the integral from 0 to 5 of ds, which we have computed to be the integral from 0 to 5 of e to the t plus 9 dt, which is e to the t plus 9t evaluated from 0 to 5. E to the 5 minus plus 45 minus 1. Everything about this part is easy, right? The only trick in these arc length problems is the obnoxious algebra that goes into grinding these things out. So you might ask, how does this show up if you see it on an exam? The way I normally like to do this is to give you a straightforward, but this actually I might expect you to be able to do. more complicated examples, I might just say set the integral up instead of actually work your way through the computation. This is on the level of something you should be able to do. I mean, I've done it in more detail than you need to. Make sense? All right. What else?
On 10.1 is number 8.
Can you describe it to me?
I can
Or show it?
easier to show.
All right. Oh no, is this like a pick the correct track or something? Parametric equations for the path moves around this particle. Find parametric equations for the path of the particle that moves along that circle in the manner described. Okay. Find parametric equations for a particle traveling it was x squared plus y minus 2 squared is equal to 16. Oh, so yeah. Once around clockwise, starting at the point 4, 2. All right. What am I doing? Okay, first thing we should do is we should plot the circle where it actually is, not centered at 0, 0, right? So one of the things you're supposed to be able to do with this is identify what this path actually is, right? So that's a circle of radius 4 shifted 2 units to the right. This gives you the shift. This gives you r squared. So you know that your center is at 2, 0, and that you're 4 units out. 1, 2, 3, 4. 1, 2, 3, 4. Then we go here, 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 6, minus 2, plus 4. Up here, minus 4. So you should be looking at, just imagine I made my plane so that all the tick marks are the same size. At least that's the path we're starting with, yeah?
Isn't it T and sub equals the minus 2 and y?
Thank you for pointing that out. Yes. Uniformly distributed x-axis I've ever just like fix this. If you think that I'm not doing a good job, you come and draw this. Practice your chalking skills. 1, 2, 1, 2, 3, 4, 1, 2, 3, 4. Okay. Center's here. Yeah, it's an upshift of 2. Thanks for catching that. So 0, 2 is the center. I go up 4 units, I go left 4 units, I go down 4 units, I go right 4 units, and I get a circle. Okay, so already, what I'm thinking is, I'm on some kind of shifted, there's going to be cosines and sines running around in here because cosines and sines are going to need to rotate us around this circle, right? But something's going to have to be shifted. Our x and y coordinates are going to have to be shifted because we're not rotating with respect to the origin, we're rotating with respect to this point 0, 2. So it wants us to start at 4, 2, which is this point right here. And it wants us to rotate clockwise or counterclockwise? Clockwise, once around clockwise. So it wants us to go this way. So my assertion is that if we can understand how to do this anyway, that I can adjust it to make it do this. If I can figure out how to write equations of this thing that rotate around the circle any way you want, we could make it go backwards by putting a minus t inside. We could start it at a different time value by shifting t forwards or backwards. I just need to know some place to start doing this. Okay, so I already know here that what I would want to do is I want this, the easiest way to think about this is I want x to be cosine. Something, right? So x is going to have to be some kind of cosine of t, and y minus 2 is going to have to be some kind of sine of t. And we're going to have to adjust this because what is the, how far away from the origin or the center of the circle is cosine of t? How many units away? Always. So like this particular point right here falls in a circle of radius what? 1, the way I've written it, right? that squared and this squared together will fall in a circle of radius 1. I'm sort of hamstrung by the fact that we haven't done polar coordinates yet, so I can't tell you the r cosine theta, r sine theta transformation. But let's look at what this does. So what the 4 is doing in here is it's stretching the unit circle that this has inside of it. It's stretching that circle from radius 1 to radius 4. When I put t equals 0 in that, what point comes out? Well, if t is equal to 0, I get a 4 out of this one. And if I put 0 in here, I get 0 out of this one. So at t is equal to 0. Notice, I'm not saying I knew this was the right answer going in. I'm just telling, like, my process of exploration here is I not got to know where this starts so I can fix it if it's wrong. Because what's going to, well, I'll show you why in a second. So I put in 0 just to see what is even happening in this thing. You put in 0, you get out x is equal to 4, and y minus 2 is equal to 0, which means y equals 2. Oh, sweet. Okay, so that equation right there, when I put in t equals 0, gives me the right starting point. Right? But what direction does this travel? When I put in t, so say t is equal to pi over 2, so I move forward in time, what point comes out when I put in t over 2, pi over 2? So t is equal to 0, I was at 0.42, which agrees with what I'm supposed to do. If I put in t as pi over 2, what do you get? 0. 6. Because this is equal to 1, and 2 plus 4 is 6. That means this is rotating this direction. These equations are almost correct. Almost correct. X is equal to 4 cosine of t, and y is equal to 4 sine of t plus 2. Almost, they get you the circle and they get you the starting point in the right way, but they don't get you the rotation in the direction you want. So how can we reverse it? Put a negative in for the t, right? Negative t will flip the direction around backwards. So instead of traveling from, like, in the counterclockwise direction, I could instead write x is equal to 4 cosine of minus t, and y is equal to 4 sine of minus t plus 2. And I can actually do one better than this. You guys remember that cosine is an even function? So cosine of t and cosine of minus t are the same. And sine is an odd function, which means the negative sign pulls out. So the best sort of simplest version of this answer would be x is equal to 4 cosine of t, because cosine is even, and y is equal to minus 4 sine t plus 2, because sine is odd, which lets you get that negative sign and stick it out front. And we should verify this is traveling in the direction that we want. What is this value of this equation when I put in t equals pi over 2? Well, that's still 0, right? But when I put pi over 2 into this, I get minus 4 plus 2, which is negative 2. So when I take these equations and I evaluate them at t is equal to pi over 2, I get out the point 0 comma minus 2. And that means that we're going this way to pick this point up right here. This idea of reversing the direction of travel with a negative sign is a really important idea in parametric equations. That make sense? Yep. Yeah, this is completely correct. This is the only reason I even did this was because if the answer key showed up, it would probably write it in this form. But you can put this into WebAssign, it will be completely correct. If you were for me, it would be completely correct because this actually shows that you understand, oh, I need to reverse the direction I'm moving, so just flip the key around backwards. Right? This is the more natural way of thinking about this. Yep.
Is that a problem? Say you have to travel clockwise?
It did say you had to travel clockwise too. Yeah. If it didn't specify order of movement, you could have just said, oh, well, let's just let t go from 0 to 2 pi. Right? And that would get you around the circle once. But if it specifies an orientation, then I have to tell you, okay, well, I have to make sure I know what direction things are going. And that's why, I mean, there's no way to do this other than to either compute a derivative or to pick another point further along and see which direction you've been traveling. Yep. For the halfway counterclockwise? Yes. Okay. So as our base equations here, so here's what we know right now. We have this case where we have x is equal to the 4 of cosine t and y is equal to 4 sine c plus 2. This particular one went counterclockwise. It went counterclockwise, and it started at 4, 2. And as I go from 0 to 2 pi, it goes around once because that gets me all the way around the unit circle. I didn't say that over here, but that's also part of this. One rotation from 0 to pi. That was sort of our starting equation. What we did was we took that and we modified it into this one. I'll just make it absolutely clear what's going on. And what did this one do? This goes clockwise, starts at 4, 2, and goes once around when t is stuck between 0 and 2 pi. So the only thing that changed here was the direction we were traveling. The speed of rotation was the same. One rotation happens between 0 and 2 pi. So you want to go counterclockwise, but only halfway. Ah, okay. So you have a slightly different equation. So we have two things to deal with: a different starting point and the rotation, right? Okay. So on the basis of what we have here, if I wanted to start at this point instead of that one, what would my initial t value be? Just imagine you're starting from the base case, right? Because it's either the counterclockwise case or the clockwise case. Counterclockwise says, if that's t equals 0, how do I start there? You guess? So if you start at 0 and you go all the way around the circle, you get back here when you get to 2 pi. Pi over 2 would get you to this point right here. You can check that. If you put pi over 2 in, because it corresponds to the angle that you're hitting when you get there, right? So you can just imagine, I mean, it's going the same speed all the way around. If you start at 0 and you end at 2 pi, this is where you pass through pi over 2. So one way to do that problem is just to change the values of t that you consider. So if you let t start at pi over 2, then you're starting here. And we want to go halfway around. So what's the end value of t that I should use? Three pi over 2, right? Yeah. So 0, pi over 2, pi, 3 pi over 2, 2 pi, right? If you put in 3 pi over 2, you're going to get out the bottom of the circle. In this particular, we've set this up in the easiest possible way where the cosine and the sine act like the unit circle, which is why we're allowed to use the regular angles. So this restriction of t is going to give us a half circle because it's only an interval of like pi. It's not all 2 pi angles. It's just pi of them, right? And as long as I put it into a circle that's turning in the right direction, I'm going to get the right motion here. So do I pick these equations or do I pick these? I should pick the first because those are the ones that are turning counterclockwise because that's the way the unit circle is set up. So this domain coupled together with these functions these are going to give you a circle that starts here and goes this way and stops there. Now, an interesting exercise would be, how would you write down the equations if it went the other direction and it started here? Or if it started here and it had to go this way instead? What if I asked you the same question, but I said, now make it go clockwise instead of counterclockwise for a half circle? Okay.
Yeah.
Ah, actually, so there's a, if it wants it between 0 and pi, So if you need to shift the domain, one way of doing that would be, how could you take this domain and shift it so it went from 0 to pi? What would I have to do to this to make that happen? I'd have to subtract pi over 2. So if I went from 0 to pi, and I have to subtract pi over 2 to do that, what do I have to do to these t values? To make sure the values are the same. Well, if you put a 0 into this right here, the number that comes out is 0, but I don't want to start at 0, I want to start at pi over 2. So I don't subtract from t, I add to t to shift it. If I subtract from the domain, I'm shifting one way, I've got to shift the function the other way. So this should be x is equal to 4 cosine of t plus pi over 2. And y is equal to 4 sine of t plus pi over 2 plus 2. And if you actually look at the values that you get, when you put pi over 2 in here, you get pi over 2 and pi over 2. When you put 0 in here, you get pi over 2 and pi over 2. That's how you make sure that they line up correctly. So we haven't changed the function. This is called a reparameterization. We just slid the starting point to make sure the domain works. Make sense? Oh, okay. So WebAssign is going to do something crazy here. The reason is there are identities that tell you what cosine of t plus pi over 2 and sine of t plus pi over 2 actually are. I'm willing to believe it will accept these answers the way they're written. And somewhere deep in your mind, you should think, oh God, shifts of pi over 2, that's like taking a cosine and moving it and turning it upside down, and you get a sine function on the other side, right? There's these shifting identities like pi over 2, which I don't care if you know. WebAssign might want to tell you the most elegant form of the answer, but it doesn't matter. Try it like that, and if it doesn't work, let me know. Oh yeah, I was talking about this before class. If we get to the point where there's anything other, so like we're going to be moving into polar coordinates, and people are worried about how much trig they need to know, how much trig you got to be carrying in your head. I want you to know the Pythagorean identities. So sine squared plus cosine squared is 1. And I'd like you to know the half angle or the double angle identities, which is how you get from cosine squared to something you can integrate, right? Cosine squared is 1/2 plus cosine of 2x. You need to know those. Anything else, I'll just give you. If I don't have it memorized, I don't care if you do. I don't. I have to look up trig identities every time I use it. I just don't care. I'm not going to clutter my brain with that. Okay, take a look at it after class. What I would consider this to be an incorrect answer. So. Anything else? All right, so let's finish up section 10.2 so you guys can finish up your homework. We only have 2 ideas left. So we're going to do the rest. This is fine, actually, because it means that I can save polar coordinates for a completely new lesson. So the rest of 10.2 is concerned with integral formulas that go beyond the arc length formula. And the most basic one is the computation of area from parametric curve. So I'm going to draw a picture. There's a function. The book calls it capital F because it wants to use lowercase f for the x function that defines the x coordinate. There's capital F of x. And suppose that I give you an A and a B. And I say, I would really like to know how much area is contained in here. How do I write that down? It's like the beginning of calculus 1.
Integral from A to B of f. Yeah.
I'm going to be a little bit more precise than you just because I'm going to try to make a point later. But yeah, the integral from x equals A or x equals B of f of x dx. This is a representation of the area contained underneath the function. What is this called, by the way? This is a name. This relationship has a name. It's so important, they said it was fundamental. Part 1. I mean, really the evaluation of these things. Yeah, the idea that area is connected to antiderivatives and functions is the fundamental. All right. So we're going to use a really clever substitution to turn this into an integral that works for parametric equations. And I mean by substitution, I mean u substitution. That's all it is, u sub. So imagine that you're staring at this behavior right here, but you know that f has other definitions. This is the basic picture, but also x is equal to f of t for some function f of time, y is equal to g of t, and y is equal to f of x. After all, that's the picture here, right? I mean, to say capital F of x is really to say that there's some function that's spitting out y values in terms of x. So we have all this information, and I want to turn this integral into a dt integral. That's the game. How do I get a dt integral out of this? The answer is I just use u substitution. After all, x is a function. So let u equal x, which is really f of t. Remember, the goal is to get a dt. The goal is to get a dt integral. And this is the trick that we can use to get a t into the picture. Well, what u substitution says is, after you compute u, you got to compute du. Well, du is dx, but I have another expression for dx. It's f prime of t dt. That's the way you do this when you do u substitution, right? The derivative times whatever the variable is. This is a chain rule. Okay. Let's see what that did to the original integral. Oh, I guess I should also point out here, we got to figure out what to do with the a and the b, and we'll get there. Okay, so we're not changing limits of integration yet, but we'll get there. With this substitution, we're looking at this. F of u, sorry, f of u times dx. The dx was substituted out for du. But I know what f of u is. It's just f of x is y, which is g of t. F of x is y, but y is also g of t. So I can just write g of t right here. Because this is, the connection is y is equal to g of t and y is also equal to f of u. So I'm running through this equation right here. If that makes sense. And what's du equal to? Well, du is f prime of t dt. So the game was to try to figure out a way to get the dt's in there, and that's why I did this replacement. Why I took the y this represents. Remember, this is just y. And replace it with y equals 2 as a function of t, because I need this dt integral. Now the last thing I need to do is I need to figure out what the hell to do with a and b, because running around in the background here, I still have this x is equal to a and x is equal to b. If you were doing this in a concrete setting that you've seen before, you would solve an equation where you plug the a value in for x and figured out the t that made it happen, right? So instead, you just state the following. Suppose that f of t is equal to f of alpha is equal to a, and then f of beta is equal to b. So it's just the t value that produces a and the t value that produces b. Because remember, the equation that's running around in the background here is the x values are equal to f of t, right? Since x is equal to f of t, if I put in a right here, I better be able to find a t that produces that a. Right? It better be the case that if I stick an a right here with this known information, I can find a parameter that does that. So symbolically, I'm just putting a in for x and finding the t that it came from, and putting b in for x and finding the t that it came from. And so the final part of the substitution is to say that this is equal to, here we still have x is equal to a, so x is equal to b, and that turns into t is equal to alpha, t is equal to beta. This is less bad than it looks because generally you'll just be given the starting parameter and ending parameter. There's a derivation of the formula for area using just this same idea. We've derived a formula for area in terms of parametric equation. It's weird, right? I mean, this is an odd formula. At least it seems odd to me, but really it's just an expression of the chain rule. So we should compute one. Let's just see. I mean, what sort of things might we test? How about x is equal to the cosine of t and y is equal to the sine of t? Well, let's just suppose that t runs from, I don't know, 0 to 2 pi. I already know what that area should be. It's a circle of radius 1. It's the unit circle. What is the area enclosed in the circle of radius 1? There's pi. I'm hoping that when I do this, pi comes out. And the picture that we've drawn is this. Well, that's radius 1. And so the area should be pi. What the formula says to do is, I integrate from my initial t value to my ending t value. And then I need g of t, which is the y function, times the derivative of x of t. And now we just get into like a pretty bog standard how to integrate trig functions type integral minus sine squared of t dt. Oh, by the way, you didn't think you could forget how to integrate sine squared, did you? Because the book loves trig functions. All the interesting examples in calculus come from trig. So do remember, please, that when you do this, you have to replace sine squared with 1/2 minus 1/2 of the cosine of 2t. That's like the standard trick. Dave is shouting about half angle formula too. It's nice. But you can't integrate this in either way. So this is you should have that identity mechanism because it will make your life easier. Minus let's see, 1/2 t minus 1/4 of the sine of 2t, evaluated from 0 to 2 pi. Something weird happens when you do this though. When you put the numbers in and calculate this, you get minus pi. Why? Why does minus pi come out? It's the negative of the answer I want. Why? Because the sign you get depends on the direction that you travel. So this is an oriented area. You can imagine that what you're doing here is you're integrating somewhere opposite the natural direction of integration. So since negative area is illegal, you just say it's pi. You might actually compute this the other direction where you put the negatives in there and see if you get the opposite. Another way of doing this is you could think if you integrated just a half circle, you know the area is going to be negative because it's like you're integrating backwards on the x-axis. That's really what's going on here. So your integration is running in the wrong direction. All right. So that's area. Those are not difficult, but they do require you. And this is when you got to remember. So let's actually pile up what we know so far. So what do we need to know in 10.2? The ideas of calculus. So dy dt, dy dx was equal to dy dt divided by dx dt. I'm sure everybody in here remembers already after just one day that d2y over dx squared, the second derivative is d by dt of dy dx divided by dx dt. So the second derivative had this weird computational formula. And that the integral from a to b of f of x dx equal to the integral from alpha to beta of g of t f prime of t dt. Or if you like, the integral from alpha to beta of y times x prime dt. Finally, we had that length was equal to the integral from a to b of ds where ds was equal to the integral from a to b of the square root x dt squared y dt squared dt. So these are the elements of calculus. Slope, second derivative, area under a curve, arc length. We're missing one. One left. The last idea, I just write it down as a formula, just so you've seen it. If you're interested in the derivation, you can look at it. Is the standard for surface area. Integral from a to b of 2 pi. Here, there's a couple of different ways to write it. I guess I'll write the y version. 2 pi y times the square root of x dt squared. So this looks just like the one from calculus 2 when you did surface area. And remember, generally these things are, again, here where I'm considering y as a function of t. Like you've got to plug y in as a function of t. And that's it. That's the elements of calculus and parametric equations. I actually don't think they're so bad, but they do require you to remember all these things that you learned in earlier classes. All right, that's enough to do all the homework on 10.2. Next time, what we'll talk about, we'll talk about polar coordinates. If you have not looked at the behavior of trig functions in a long time, you might want to go look at that because we're going to be dealing with functions that take angles as inputs. And we're looking at a coordinate system where it's not an x and y, it's an r and theta instead. You haven't seen it in a while? Review that, it's useful. And then for those of you that are engineers, your whole future life is going to be an even worse coordinate system like spherical coordinates. Now it's like 3 coordinates given by angles. Anyway, all right, see you guys tomorrow.